Hey there, welcome to the channel. Today we're diving deep into a subject that, quite literally, keeps our feet on the ground: gravity. It's something we experience every single moment of our lives, yet it remains one of the most profound and mysterious forces in the entire cosmos. We feel its gentle pull, but this same phenomenon orchestrates the grand ballet of planets, stars, and entire galaxies. It's the silent architect of the universe, shaping everything from the arc of a thrown ball to the life and death of the most massive stars. You might think you know gravity. After all, what goes up must come down, right? It's simple, intuitive. But I'm here to tell you that the story of gravity is far stranger, far more mind-bending than you can imagine. We're going to journey from the very fabric of space-time to the crushing heart of a black hole, exploring concepts that have puzzled the greatest minds in history, from Newton to Einstein and beyond. So buckle up. Even if you're a seasoned science enthusiast, I promise you, some of the facts we're about to explore will challenge what you think you know. We're going to peel back the layers of everyday reality and stare into the cosmic engine room. Are you ready to have your mind blown by the elegant, powerful, and downright weird nature of gravity? Let's get started. Let's start by breaking the biggest rule you learned in school. I know, Isaac Newton is rolling in his grave. For centuries, we pictured gravity as an invisible rope, a mysterious pull that objects exert on each other. Newton's laws were brilliant, allowing us to predict the motion of planets with incredible accuracy, but they didn't explain why. It was like knowing the rules of a game without understanding how the game board was built. Newton himself admitted he had no hypothesis for the underlying cause. Then along came a patent clerk named Albert Einstein, who completely rewrote the rulebook with his theory of general relativity. He proposed something radical: space-time. They are woven together into a single dynamic fabric called space-time. And here's the kicker: massive objects don't pull on other objects. Instead, they warp or curve this fabric of space-time like a bowling ball placed on a trampoline. What we perceive as the force of gravity is simply other objects, like a marble rolling on that same trampoline, following the straightest possible path through this curved space-time. Think about it. The Earth isn't pulling you down with some magical tether. It has created a gravity well, a dent in space-time, and you are simply rolling along the inside of that dent. In the cosmic boxing ring of fundamental forces, gravity is the undisputed lightweight champion. It's actually the weakest of the four fundamental forces. Imagine a simple refrigerator magnet. The magnet picks up a paperclip. An arrow shows Earth's gravity pulling down on the paperclip. The magnet still wins the tug of war. That's how astonishingly feeble gravity is compared to electromagnetism. It's like an ant trying to wrestle a blue whale. Here's where things get really weird, straight out of a science fiction movie. Gravity doesn't just bend space, it also warps time. According to Einstein's relativity, the stronger the gravitational field, the slower time passes. This isn't a theory, it's a measurable, proven fact. It's called gravitational time dilation. A clock at sea level will tick ever so slightly slower than a clock on top of a mountain. The differences on Earth are minuscule, nanoseconds, but real and practical. Your GPS system wouldn't work without accounting for this. GPS satellites are in a weaker gravitational field, so their clocks run faster. They're also moving very fast. Special relativity slows their time. Engineers must calculate and correct both effects. Without corrections, GPS would be off by miles every day. Now let's take this to the extreme. Imagine you're near a neutron star. Imagine you're near a black hole. For you, time would pass much more slowly than for someone far away. You could orbit a black hole for what feels like hours and return to find decades or centuries have passed. Gravity, the force that keeps us grounded, is a natural time machine. So what happens when you cram an enormous amount of mass into an infinitesimally small space? Well, you get gravity in its most extreme and honestly terrifying form: a black hole. A black hole isn't a hole in the traditional sense. It's a warped region of space-time where gravity dominates. That gravity is so strong that nothing, not even light, can escape its grasp. Take a deep breath. Feel that? The air filling your lungs, the oxygen that sustains you? You actually have gravity to thank for that. One of gravity's most vital roles for life on Earth is one we rarely ever think about. It holds our atmosphere in place. Our planet's gravitational pull is strong enough to keep a thick blanket of gases, our precious air, wrapped around it like a protective shield. Without gravity, these gas molecules would just drift off into the cold, empty void of space. Think of the atmosphere as a sea of air. Just like the water in the ocean, this air has weight and is pulled down by gravity. This is what creates atmospheric pressure. The air is densest at sea level because the entire weight of the column of air above it is pressing down. As you go higher, like to the top of a mountain or in an airplane, there's less air above you, so the pressure decreases and the air gets thinner. We've all seen the footage astronauts floating effortlessly inside the International Space Station, tools floating water droplets hovering in midair. It's often described as a zero-gravity environment, but here's a secret. That's actually completely wrong. There is no such thing as zero gravity anywhere near the Earth. At the ISS altitude, about 250 miles up, gravity is still about 90% as strong as on the surface. So if gravity's still strong, why are they floating? Because the station and crew are in constant freefall. Imagine you're in an elevator and the cable snaps. For the few seconds before you hit the bottom, you and everything else fall at the same rate. You'd feel weightless. You could float relative to the elevator car. That's basically the ISS. But instead of falling down, it's falling around the Earth. The station is moving sideways at incredible speed, about 17,500 miles per hour. Gravity pulls it toward Earth, but its forward velocity makes it miss the ground. Look up at the night sky. Every point of light, every planet, every star, every swirling galaxy you see is a masterpiece sculpted by gravity. On the grandest of scales, gravity is the universe's master architect. After the Big Bang, the universe was an almost perfectly uniform soup of matter and energy. But there were minuscule, quantum-scale fluctuations. Some areas were infinitesimally denser than others. Gravity, ever patient and persistent, went to work on these tiny imperfections. Over millions and billions of years, gravity pulled matter from less dense regions into slightly denser ones. The rich got richer. If you've ever spent a day at the beach, you've witnessed one of gravity's most elegant and obvious effects on Earth, the tides. The rhythmic rise and fall of the ocean's water level is a direct result of a gravitational dance between the Earth, the Moon, and to a lesser extent, the Sun. It's a beautiful demonstration that gravity's influence stretches across vast distances of space. The primary driver is the Moon. Here's how it works. The Moon's gravity pulls on everything on Earth, but it pulls more strongly on the parts of Earth that are closer to it. This difference in pull is called a tidal force. The water on the side of the Earth facing the Moon is pulled toward the Moon most strongly, creating a bulge. This is high tide. But here's the cool part. The solid Earth itself is also pulled toward the Moon, more so than the water on the far side. This leaves the water on the opposite side of the planet behind, creating a second simultaneous high tide bulge over there. As the Earth rotates on its axis once every 24 hours, any given point on the coast passes through both of these bulges, experiencing two high tides and in between them, two low tides. One of the most mind-bending predictions of Einstein's theory of general relativity was that gravity could bend the path of light. Remember, light always travels in a straight line, the shortest path between 2 points. But in Einstein's universe, if space-time itself is curved, then the straight line that light follows must also be curved. This isn't just a theoretical curiosity. It was first famously confirmed during a solar eclipse in 1919 by Sir Arthur Eddington. He observed starlight passing close to the sun and found that the star's apparent positions were shifted, exactly as Einstein had predicted. The sun's gravity had acted like a lens, bending the starlight as it passed by. This phenomenon, known as gravitational lensing, has since become one of the most powerful tools in modern astronomy. Astronomers can use entire galaxies or clusters of galaxies as giant, natural telescopes. When a massive galaxy cluster sits between us and a more distant object, its immense gravity can bend and magnify the light from that distant object, allowing us to see things that would otherwise be too faint or far away. Sometimes, this lensing effect can distort the background object into arcs, smears, or even multiple images of the same object, forming what's known as an Einstein cross or an Einstein ring. It's a stunning visual confirmation that gravity rules over even the path of light itself. We've journeyed through space-time, visited black holes, and watched gravity sculpt the cosmos. We've seen how it affects time, holds our atmosphere, and bends light. We have described its effects with breathtaking precision. But after all that, we come to the most profound and humbling fact of all. We still don't fundamentally know what gravity is. We can describe what it does with incredible accuracy, but its true nature, its ultimate source, remains one of the deepest mysteries in all of science. Solving this puzzle and developing a unified theory of quantum gravity would represent a revolution in our understanding of the cosmos, potentially explaining everything from the inside of a black hole to the very first moments of the Big Bang. And there you have it, 10 facts that show just how strange and wonderful the universe's most familiar force truly is. From bending time itself to being the weakest force of them all, gravity is full of cosmic surprises. It's a reminder that even the things we take for granted are often gateways to the deepest and most fascinating mysteries of the cosmos. The universe is under no obligation to make sense to us, and that's what makes exploring it so incredibly exciting. So, what was your favorite gravity fact? Was it the idea of spaghettification, the mind-bending reality of time dilation, or the simple fact that you're in a constant state of freefall while orbiting the sun right now? Let me know down in the comments below. I'd love to read what part of this cosmic story resonated with you the most, and let's get a conversation started. The best part of science is sharing the wonder. If you enjoyed this journey into the heart of physics and want to explore more of the amazing science that shapes our universe, please consider subscribing to the channel and turning on notifications so you don't miss our next adventure. Thank you so much for joining me today, for your curiosity, and for your time. As always, keep exploring, keep asking questions, and keep looking up. So, Earth's mass is in a Goldilocks zone of gravity. Not too strong, not too weak, but just right to hold on to the life-giving mixture of nitrogen and oxygen that we call air. It's a cosmic embrace that makes our planet a habitable oasis in the vastness of space. Eventually, these clouds of hydrogen and helium became so massive and dense that the pressure and temperature at their cores ignited nuclear fusion. And just like that, a star was born. This process continued on all scales. Clumps of stars were pulled together to form the first galaxies. Leftover dust and debris orbiting the newborn stars were gathered up by gravity, colliding and sticking together to form planets, moons, asteroids. When the sun, earth, and moon are aligned during a new moon, during a full moon, their gravitational forces combine to create extra-high spring tides. When they form a right angle, they work against each other, creating weaker neap tides. It's a cosmic tug-of-war, and our oceans are the rope.